Okay, so we're back here continuing to talk about pressure and fluid statics problems, and in this video I want to look at computing the net resultant force on a structure that is submerged in a fluid associated with buoyant force. Okay, so this would be important if you were going to analyze a ship or some other object that was going to be in water that was going to have air on one side and water on the other side, or potentially any situation where you had two different fluids involved here. It's air and water, which is the most common. And the key idea in analyzing these, really, it's going to combine together the concepts from a few other videos that we've made. And that one of those is going to be buoyancy, so we have to consider buoyancy because this is air that is submerged underneath water that's going to have a buoyant force. And then we also have to think about how to compute forces on curved surfaces, which we have looked at. So the idea is the same with what we need to do here, and the key is to make this vertical cut like we talked about before. All right, so in this situation, we're trying to figure out the buoyant force here on, or the force that would be caused on the structure as associated with buoyancy here for this part that's AB. So there's really like three different parts of this shape that we would need to think about. And one of those is going to be above part A, and one of those is going to be AB, and the other one is going to be beyond part B. Okay, so everything in here, all the volume of water that is being displaced is causing a buoyant force. That has to go somewhere. Now, everything that's to the left of B, all this over here, is going to create a buoyant force on this part of the ship or the structure. Okay, and everything above point A here is going to cause a force. There's going to be pressure from this water that's pushing on it. That's going to push and cause a force here. All right, so if we're trying to understand what's happening on AB, this is going to have to deal with the pressure force pushing on it from the right, and it's going to have to deal with the buoyant force here from not only this section, but from all the displaced water that goes up here. Okay, so the air that is displaced here cannot be counterbalanced by this section of the structure. It has to be interacting with this part AB. So the key idea here is how we draw this free body diagram. So yeah, what we're going to do is we're going to make a vertical cut just like we did for the curved force when it's filled with the fluid, and now instead we'll do a different free body diagram here because it's going to have buoyant forces instead. So I'm going to do this free body diagram, and I'll draw it here. Okay, so I've got this curved bit up there, and so the free body diagram is on the displaced fluid in AB. Okay, and so this is going to have a buoyant force acting up from the displaced fluid. There's going to be some force in the y direction here to counterbalance that one that's on this object, the force here. So if you were doing a structural design, you wanted to know how much stress there was going to be, you would need to think about that. And then there's going to be pressure here from the fluid that's pushing on that one. And so that is going to, again, if it went all the way to the surface, there'd be pressure over there. But this part at the top above point A is actually going to be balanced by a force on the structure above point A. So the only part that we need to think about for AB is the part down here. So we will draw it like this. There's this force there, and it gets bigger. Okay, it would intersect with 0. So there's kind of a distributed load here acting this way from the water pushing on it. All right, and then likewise we're going to have a force in the x direction here that's on the structure that will counterbalance that pressure. So this balances the pressure force in here. The pressure force above that is balanced there, and then but the whole buoyant force here is going to be felt between AB. All right, so we can analyze this problem again using the x and y separately. A few things we need. Other pieces of information. We're going to need the specific weight of water, which I will use 9.81 kilonewtons per cubic meter because we're in metric, and I'll do it in kilonewtons here. And then we're going to need to calculate the magnitude of this pressure force And so we can figure out the area of this shape looking at it from the left and multiply it times the average pressure. And since pressure is varies linearly with depth, if we know the pressure at either end, and we can get the average from just averaging those two. So the average pressure across that area is going to be gamma H1 plus gamma times H2 over 2. The pressure at the bottom or the top plus the pressure at the bottom divided by 2, the average. Okay, and so this height here, and looking at the diagram, this is 3 meters, and then this down here is going to be 4.75 meters for the two heights. Okay. So I think that's everything we need. I'm going to analyze the y direction first. So if we do the sum of the forces in the y direction, that's going to be minus Fy plus the buoyant force, and that needs to equal to 0. And that then tells us that Fy, what we're trying to find, is equal to the buoyant force. And we know the buoyant force there is just equal to the gamma for the water times the volume that is displaced. And so Fy then has to be equal to gamma water, which is 9.81 kilonewtons per cubic meter, and times the volume. And so, pardon me, the volume here is going to be, okay, so we're told that this is a width of 1 meter into the page coming towards us, and so we need to multiply the 1 meter this way by the area of this shape, and so that's going to be a 3 by 1.75 meter rectangle plus a 1.75 meter radius quarter circle. So I'm going to multiply by 1 meter here, both of those chunks, and then I need to multiply that one by the sum of the rectangle and the area. So I've got a pi over 4 times r squared, which is 1.75 meters squared for this part of the area, and then the other one is 1.75 meters times 3 meters. Okay, and so that will be the area in square meters. That makes it volume, and that's times the specific weight, and so we get that the y component of the force is equal to 75.1 kilonewtons. Okay, that's going to be the stress here in this direction. And then in the x direction, sum of the forces in the x direction is going to be Fx, the part from the structure, and then minus P average times the area of that face. And so the area, again, it's 1 meter this way into the page, and then the height of this is 1.75 meters. So that's going to be the area, and we know that the P average is here, and we can factor out a gamma. So we get that needs to equal 0, so therefore Fx is equal to the area times gamma over 2 times h1 plus h2 times the width into the page. And so the area is the width into the page times 1.75. So let's see, this is going to be, gamma is 9.81 kilonewtons per cubic meter. The area is 1 meter by 1.75 meters, and then the gamma needs to be divided by 2, so we have a half, and so that's the W, that's the half, that's the gamma. That leaves H1 and H2, which are 1.75, sorry, no, it's 3 plus 1.75 over 2. I've already got the 2 there, so it's, sorry, it's 3 plus 4.75 meters. And that then gives me that this should be equal to 66.5 kilonewtons. That is the force in the x direction, if I've got that right. So, yeah, we'll pick up there in the next video.